do something a bit different. So instead of actually going through any particular problem, let's study. Um, and it helps to study by, as Tim Ferriss would say, deconstructing a lot of problems. And unfortunately, a lot of times to spot patterns and actually deconstruct algorithms, you just need to see a lot of solutions. So in this video, I'm going to deconstruct both depth first search and breadth first search. And the goal of this video is more towards code templating as opposed to teaching you how to spot those problems to solve, because those are two different skills. So the goal of this is so that you can sort of memorize particular elements in BFS and DFS. So it's much easier to visualize, and then you can just type it out from memory during an interview. Because figuring out the problem is hard enough, but then the second layer of hardness comes in when you actually have to convert those ideas into code. In this video, I will break down DFS and BFS searches, so you know what's kind of common in any and all DFS, BFS search. So then next time you're in an interview and you're like, oh man, I have to search this, but it seems like a burden to implement DFS or BFS. You can at least use this framework to reduce your time and just type some of it out from memory, and some of the heavy lifting is done for you, and all you have to do is to kind of fill in spots in the DFS BFS template to complete the problem. And then that just makes it a lot easier, because if you have the challenge of solving a problem, you don't also want to take on the full burden of challenge of like implementing brand new code. And if it's not DFS BFS, then there's some other patterns you can study as well, but not 100% of the time it'll be BFS, DFS, right? But without further ado, let's take a look at some BFS, and then let's take a look at some DFS, and then let's take a look at how that is applied to this graph search problem. So in this BFS problem, it just says find the number of islands, islands being denoted by ones in a two-dimensional matrix. And I guess the problem itself isn't that important. What I want you and also future me to look at are these following elements. First, you have to loop through your matrix, obviously, so your graph, and then inspect each node. And then you're always going to, in breadth first search, prevent infinite loops, have this seen or visited set to keep track of all your visited nodes. And then you're going to have some condition here. This condition generally will have visited in it, but then the rest of this is, this will always be in a BFS. This is the minimum requirement. But then on the left-hand side of this and, it's just whatever the problem has. In this case, the problem says, well, the valid nodes are when mat of ij is 1, so then we have to tack that condition onto this visited, right? But this is kind of orthogonal BFS and just more specific to the problem. As is this. So really, you just need to understand that there must be some check that you need to do at the beginning of this, like as you're iterating through your BFS, there must be some condition that you check, plus that it's not visited. Now, right after that, you're basically always going to see this visited and q.append of whatever your node is, or however you symbolize your node. In this case, your node is represented by the row, comma, column tuple. And then BFS will always have this queue structure. And in this queue structure, you're just going to always pop it, and then you're always going to visit its neighbors. And so as you visit its neighbors, you're in this specific case, you're generating some coordinates, and then you're checking those coordinates are within bounds. And that's more specific to this problem, because the problem is presented to us in a matrix. But once again, what we want to do and is required for all BFS is going to be this neighbor represented by new row, new column isn't going to be in your visited or seen set, and this part is also specific to this problem. But basically, yeah, like the second condition is going to be something that's specific to a problem, and then you have to not forget to check that it's not that the neighbor hasn't been already visited. Otherwise, you get infinite loops. And here, you also must have the same pattern for these two. These two are required, and the reason, so just memorize like these two lines. So TLDR, memorize that you have to loop through everything. That's easy enough. Memorize that you have to have some condition check plus you're not in visited. And then memorize that you need to do this scene.add or visited node.add, and then also queue.add up in here. And then also memorize that in like while the queue isn't empty, then you have to pop something. When you pop something, you search its neighbors, and when you search its neighbors, you're gonna have some problem-specific condition plus this visited thing. So the reason why you need both of these here and here is here. You're seeding a node to search in a cluster, in this case an island, but it'll work for anything basically. But then here you need both because q.append says add the neighbor, so then I can go ahead and when I pop it next time, I can go ahead and look for the neighbors. So that's why it's important to do q.append here, because otherwise you won't be searching your breadth first search. Yeah, and then visitor.add is important to avoid infinite loops. So that's all these two lines are for, and they kind of pair together quite well. You wouldn't have, I can't really imagine a breadth first search algorithm where you do one without the other. So you must have these two go together. So if you do like q.append, just then reflexively say, oh, I did q.append, I must also do visit.add. Okay, so in sum, the structure is just, this for loop, condition check, your queue and scene adds, and then your while your queue, look at your neighbors, some logic that's specific to the problem, but you always have this pop queue here, otherwise, yeah, like you need a node to find neighbors from. This is the neighbors that you're finding from, and then this is generating the neighbors, and then this is checking the neighbor's condition, always having this visited, and then this here is just a copy paste of this, except the coordinates that you're checking and what you're appending is of the neighbors of this node, right? So these are the eligible neighbors of this node. And then so that's BFS. DFS, there's this solve n queens. I won't go into it, but basically, yeah, I mean, the problem in and of itself is not that interesting, but the structure of DFS is interesting. So DFS is in some ways simpler, in some ways harder. So it's simpler, it's shorter, but it's harder to grasp. So with DFS, just ignore this. This is really problem specific in formatting a string for the output. But in DFS, you're always going to have an if statement or your base case up at the top, and then you're going to have a for loop that visits its neighbors. So for example, in this queen problem, this is the base case saying like, well, if I, so the high level context is on a, n by n chessboard, you can place n queens, find all the distinct board configurations. And then so in this depth first search, if we say, well, if we placed, 8 queens, let's say n is 8, and we place 8 queens, then we'll just append it to the answer and then just return stuff. And then propagate that up. So that's always like the base case, and the base case is problem dependent, but the base case always has an if statement, right? So, just know that DFS, the first thing you do is either an if statement or you might also instantiate some variables up here. And then after this base statement, after this, it's missing for, I think, well, yeah, it is in this problem. After a base case, then you go ahead and visit its neighbors with condition check. So this is very, very similar to BFS, right? BFS is like, this is my current node, and then this is the logic for visiting neighbors. DFS, same thing. Yeah, this is for visiting his neighbors. So this is saying, this is just a condition check that's very specific to this problem. But here, since you're DFS searching, this queen on columns just says that I didn't already place a queen on that specific column in the chessboard, but you could think of this as your seen or visited set, and then this is just whatever candidate you're trying to place, right? So this just prunes out anything that's not eligible to be placed. In this case, you're checking diagonals and stuff like that. It doesn't matter though. But just know that in DFS, you start with an if-based case and perhaps some optional, like sometimes answer will be inside it if you don't want to have a global variable. Yeah. So basically, yeah, for all the columns, then you're going to go ahead for all its neighbors. You're going to do this check. And then if the neighbor is eligible, then you do a DFS search. And then so inside this call, then it'll also, look at its neighbors, right? So in a sense, like there's quite a nice symmetry between DFS and BFS. DFS uses a queue for that sort of neighbor to neighbor search. DFS just uses a call, right? But you can also see that there's a for here and there's an if here. And here there's a for here for its neighbors, and there's an if here to check the conditions. So it just kind of depends on what your mood wants. But DFS and BFS can be both used to search, any graph problems. Some might be a bit easier. But let's look at more DFS. For example, in this permutation, you have top down or bottom up permutation. So the base case happens at the bottom, and then we all the leaves are the base case, and so we start out with nothing, and then we keep appending an element to the permutations until we reach length of n for the array, and then we just propagate the answer up top. Here it's top to bottom, meaning each DFS calls a lower layer, and then the lower layer returns some sub answer, and then I will go ahead and add to the answer here. Now this is, so this is more problem specific, but again, let's kind of go through the structure of the code. So that, both of these are DFS, and you'll see both of these have this if statement and if statement for base case first, and then both of these have instantiations for answer inside. So if you want to accumulate stuff with a global variable, you can. It's okay. But this is another way to do it, is you would just have the answer from the bottommost level and then just propagate it up by plus equal. So all of its children will have some answers, sub answers, and then it will just take all of its children's answers and then just append it to whatever current answer and then propagate it up. So the next level higher can just propagate and bubble that answer to the root. So that's one way to do it. But what I want you or me in the future to notice is, again, it's just if statement, and nothing special here. We're just visiting its neighbors for this. And then we're just checking a condition for its neighbors. In this case, we don't want repeated elements, so it's just checking, hey, if I9 R, you could almost say that this is your visited or seen node, or your seen set. And then this is the same thing. This is slightly different. So instead of an if statement, I just go ahead. So I just go ahead and exclude the current index. So the index is 0, so let's say index was 2, go to 0, 2, and then 3 to blah, so then you exclude index 2. So this is like an implicit if statement here, and so I don't include it in the passing to the lower layer, and this does the exact same purpose as this. And then here, instead of plus equals, I just do answer.append, just because of the formatting. So my filter is actually here, implicitly in here, but it could have, I guess it's harder to write an if statement for this, but it serves the same purpose as this. This has an if statement like in here, so this whole thing basically does the same thing as this if statement and returns something here. This collects a lower layer answer and I process the lower layer answer. With this is very problem specific, so it doesn't matter. But then once I process it, then I return an answer and bubble it up to the next level. But yeah, like you can see in DFS here, base case if statement, neighbors, check of conditions. And then here, base case, neighbor check, neighbors. In this for loop, look at the neighbors and then check the conditions. Same thing here, base case, for loop to neighbors, check the conditions implicitly here, and then problem specific. And then so now let's bring it all together, BFS and DFS. So in this particular problem on LeetCode, it's just basically saying like you want to merge some accounts, but at the end of the day, time doesn't matter what the problem is. What matters is that we create a graph that we can search through. So this graph is going to be basically graph of each node, neighbors, basically. Okay. So graph of each node is, and then the key is the node, and then the value is neighbors. This is another pattern I've seen quite a bit, where basically they give you, let's say, a 2x1 array 0, 1, and then it says node 0 is connected to node 1, and that also means that node 1 is connected to node 0. You run the problem of like, well, how do I traverse this? Because BFS and DFS are directional, meaning it matters like where you start, because where you start is going to update the seen or visited set differently. So a lot of folks on LeetCode just do this pattern, which is just loop through the entire undirected graph and then add direction to it. Namely, like, this from points to this to, and then this to points back to this from. So it's basically breaking one edge into two edges that's pointing back at each other. And then the algorithms, either DFS or BFS, can solve this, and then both of these are not solutions. Ignore this part and ignore this part. These are just post-processing for the specific problem. But here it's actually quite simple. Clusters problem specific, but yeah, like if male and seen return, so don't do anything. This is kind of like the base case here, and then for this is even more elegant for neighbor in the graph.mel than you do DFS. So here the base case is the check in this scene thing. Yeah. You could also, I guess, if you really want, move this if statement down here. And then do like scene.add if it's not in scene, and then do the thing. But actually, no, that won't work. Yeah. So basically, if this node doesn't exist, is the base case. If this node doesn't exist, then obviously there's nothing to search. But if this node does exist, go ahead and look at its neighbors and then DFS it. And then this is problem specific. Well, this isn't problem specific. You're adding to a scene.add. So this DFS is kind of like a mixture of your BFS and DFS. So you do have a global sort of scene set here. And so this serves as your base case and condition check, but it's still like an if statement, and then under if statement is this for. So the neighbor check is taking place in the layer below as opposed to here, but yeah. And then, sorry, this is problem specific, but this, yeah, I mean, I guess scene.add could be problem specific or not, because here I'm like checking if not in something, and then here, yeah. But here it's the base case, and then here, yeah, I guess depends on how you want to structure it, but your base case, I guess, could also be the check. And yeah, how this works is basically kind of closer to BFS in my opinion, but so instead of using a queue, it still just uses scene.add, and then it just visits its neighbors like this. So if a node exists, visit its neighbors. If a node doesn't exist, return. And if a node does exist, go ahead, add it to the visited, and then this is problem specific, and then just add it to, just update the answer here. All right, BFS is somewhat similar to before. Again, we iterate through the graph. In the search islands case, is a 2D array, but it's still, I guess, just a graph. So iterate through every element, make sure it's not seen, and then we do this double thing, as you'll see in here. And then when you do this double thing, problem specific, and then you do this here, and then you have your while queue, right? Here you do this thing here, and then you have your while queue. You pop it here, and then search neighbors. So you pop it here, and then you search neighbors, right? And then here is just the pruning condition to see that it's not in the scene set. And you'll see that these two are the copy paste of these two lines, very completely symmetric, as these two lines after condition check is the copy paste of these two lines. And yeah, and then this is kind of problem specific on how you want to format the problem. In this case, you do need to add an answer here. In the island case, you don't have to add an island on every neighbor. So yeah, I mean, as you can see, it's like when you break it down like these elements, like, oh, I just do this, while queue, pop for neighbor, check condition, paste this again, and then add a condition check here, and you're good. And then DFS is like base case, and then for, and then some condition check here if you want. Then you're in pretty good shape, because now in an interview, like what are like the few elements you need for BFS and DFS, and you can just kind of, even if you don't have this 100% memorized, like seeing these patterns, like you're just gonna know, like at least have the confidence to say, all right, I'm just gonna BFS this, and then do it. And then depending on your comfort level, you can also construct DFS. DFS is more elegant, as you can see here, but there's so many variations of how you could probably approach this, top down, bottom up, or whatever, what have you. Some implementations significantly harder than others, and in my opinion, a little harder to understand than BFS, but you can BFS or DFS. Some situations call for DFS, and some situations call for BFS. If DFS is very easy to understand in your brain and visualize, I would say just go for it, impress the interviewer, because you can like think recursively or whatever. But then also, it's quicker to type out than all this boilerplate. Yeah. But if your problem requires you to have layer by layer information, so for as an example, I want to count the minimum steps from one node to another node, then you're best off with BFS, because your fringe layer, or like the new layer that you're exploring, needs to be able to infer information from the previous layer, or like all the neighbors basically need to infer information from this node, right? So here it's very easy to access, because it's like right here, and then you just access current underscore email dot whatever, and then you can build some formulas inside here. Here it's quite a bit harder, and I mean, you can do it certainly, but it's definitely a bit harder for me, at least, to think about. Like for each neighbor, then you have to return some specific tuple or triplet of something, and then you post process it here. I guess it really depends on your comfort level, but those are kind of like decoding template patterns for DFS and BFS. Yep, and that's it. I hope that helps and will shorten your implementation time in your interview.